next speaker is our first guest speaker, who is very happy to be here in Poland for a few reasons. One, that he had the opportunity to have dinner with Zef Hemmel. That's correct, right?
That's correct.
Any one of you knows Zef Hemmel? He used to work with us at STX Next. Exactly, exactly. So you already have a mutual friend with our next speaker. The second reason why Jan is happy to be in Poland is because we're one of the few nations that can actually pronounce his name correctly. Jan is a developer evangelist for Internet of Things and principal applications engineer at the company called ARM, and his presentation will be killing two birds with one stone, because on the one hand we'll be talking about Internet of Things, but also on the other about machine learning, covering two of the technologies that we want to focus on during this year's conference. So, without wasting any more time, please welcome to the stage and give a round of applause to Jan Jongboom.
Woo! That was a very nice introduction. Thank you. So today we're going to talk about machine learning on the smallest of devices, Internet of Things devices. I really like this animation because it's made by Google, where they try to teach a stick figure how to walk, and it gets forward, but in a completely different way. I think that's one of the really one of the really interesting parts of machine learning. You can get very illogical conclusions from what happens, but that's actually correct. So, as I said, I'm a developer evangelist. Developer evangelism is a really weird job. It's kind of a new job. I want to convince people that whatever is happening in the development world is really cool. I'm working with clients to prove that, but I'm also teaching and doing workshops like this. So this was actually last year in Tanzania, where we were teaching at the University of Arusha, working together with mathematics master and PhD students on bringing machine learning to problems that they face in Africa. So one of the things we built was actually a kind of a Fitbit for cows that was using skin temperature and movement data of the cow to predict when a cow was in heat or when a cow was starting to get sick. And it's really cool. It's like a problem that I would never think about. But in Tanzania, knowing when a cow is in heat is really important, because a semen sample is $2 to $4, and that's a lot of money for these farmers. And applying a little bit of local machine learning on a cow, actually improves their quality of life tremendously, and that's really cool. If we look at the history of machine learning, it all starts with games. Like a lot of things start with games. Development in GPUs, development in computers itself start with games. This is a movie 21. It's a movie about the MIT blackjack team. Has anyone seen this movie? Oh wow, it's a lot. Really fun movie. And this was about MIT students actually gaming blackjack by counting cards. But a lot earlier, in 1954, MIT actually did something else with blackjack. One of the first actual use cases of machine learning. Because back then they ran millions of hands through a computer to try to optimize playing strategy. If anyone has ever used one of these scorecards for blackjack, which basically tells you when to hit and when to stand, this was actually developed over 60 years ago by these MIT students doing all the simulations on the blackjack table. And that's something we still use today. It's kind of like a first in machine learning, actually simulating stuff that happens in real life on a computer. In the same decade, this guy, Arthur Samuel, wanted to build a computer that he could play checkers with. So he started building this, and a bit of like an arithmetic function by actually creating a computer program that could play checkers. But about 7 years into development, in 1959, he wrote a paper stating some studies in machine learning using the game of checkers. It was the first time that the term machine learning was actually being coined. At that point, he already realized that if we would take more like a learning approach rather than try to write all the rules in the computer program, it could yield vastly better results. And so he started developing this first machine learning algorithm to play checkers with, and in 1962, a computer beat a professional checkers player for the very first time. It's cool. It was the first time that a computer could actually beat a human in a moderately difficult game, already 60 years ago. a year later, this was Donald Mitchie, created a computer, but not an electronic one. And he introduced the word reinforcement learning. Reinforcement learning is a model where the computer learns from its mistakes or its successes and then adjusts the model itself. And without a computer at hand, Donald Mitchie actually created a Matchbox computer. So all of these are Matchboxes. There are over 700 of them, and every Matchbox has state in it. And he used that state to actually play tic-tac-toe against itself and teach the model from its mistakes. It is really cool. I'll go into a little bit of detail about that. Then, of course, 1997, Garry Kasparov. This was for me the first time that I thought, holy shit, computers are, taking over the world. Skynet, everything. Kasparov actually lost against Deep Blue, the IBM chess machine. That was groundbreaking. No one expected that to be possible in 1997. Then, of course, last year, AlphaGo. No one expected Go to be possible to be conquered by a computer. And Google actually managed to do that also 10 years before anyone would think this was possible. And I think this is absolutely tremendous. I think it's brilliant. However, when we think about this, when we think about beating AlphaGo, beating chess, we're thinking about really large data centers full of computers, full of GPUs. If you look at the latest version of AlphaGo, Google actually had to develop custom silicon, a tensor processing unit, and place 5,000 of them in a data center consuming 30,000 watts just during the training, and have this model play games of Go against itself. And while this is absolutely cool, it also means that it's kind of out of reach for everyone here. Like, personally, I don't have the budget to develop custom silicon, let alone build a complete data center. That's not me. And it has a couple of other downsides as well, because if this is the approach that you take to machine learning, that also means that you need to do this centralized. You need to send all this raw data directly to a data center, and that's something that I might not want because of ethical issues or because of privacy issues. For me, a lot of the power of machine learning is not in these big centralized algorithms, it's about giving me local control about things. I want the stuff in my house to be smart. If I'm going to have a camera somewhere in my house, I would like the camera to actually be able to detect intruders and then send a signal directly to my alarm system rather than uploading all my raw data to Google, do all the processing there, do it back. And all without building my own data center in my own house, preferably. So when we were looking at this in our team, it's like, where do we want to apply machine learning? Where do we think we can actually add the value? And we're looking at like the actual devices that are being deployed within our houses, in our offices. We figured we needed to be able to run this on a microcontroller. So this is the Nest, the Google Smart Thermostat. So the Nest itself is a pretty small device. It's 8 centimeters in height, like this. But the actual brains of this thing is this 1 by 1 centimeter little thing in red, which is the microcontroller. And these are ubiquitous everywhere. Last year, ARM shipped, or 15 billion chips shipped with ARM technology, and then most of them microcontrollers. These are everywhere. I would really like to, get my machine learning algorithms running in here, because that means that I can make every device smart without streaming all my data somewhere or building a big data center in my house. Now, of course, they're small and they're cheap, but they also are very slow and they have very limited RAM. So we started thinking, okay, well, before we needed 5,000 TPUs in a big data center to run these machine learning algorithms, can we scale this down somehow and actually get this to run on a microcontroller? So to show you how that might be done, let's look at actual reinforcement learning and what happens when we run a machine learning model. So this is the Matchbox computer that was shown in 1963. And let's see what happens if we're going to play a game of tic-tac-toe against this computer. So every box here represents a state. So every box has a little diagram that says, well, if there's 2 X's on the left and there's an O in the middle and an O in the right top corner, go look in this box. And there's stuff in that box. And what's in that box depends on the state of the field. So we have 5 possibilities, and we're going to color code them here in green, blue, pink, red, and dark blue. And at the complete start of this program, when nothing is being trained yet, we put 2 marbles into this little matchbox. So in this case, there's 10 possibilities, 10 marbles in this thing. And now I want to make a move. So what I do is I randomly pick 1 marble out of the box, and that's the place where I'm going to play my X. So in this case, I put it here. Now, of course, this is a bad move, because the other player can win directly. So to determine what we need to do, we keep the matchboxes open for all the states we do, so 4 matchboxes over the time of the program. And then depending on the outcome of the game, we apply some rules. So in this case, if we lose, we don't put the marble back. If we draw, we put it back. Or if we win, we actually not put 1 back, but actually 3 back. So in this case, the other player gets 3 in a row, tic-tac-toe. We lose, and in this case, we don't place the marble back, so we have 9 marbles in the matchbox. So let's say that we encounter this state again at a later point in this program. I'm doing exactly the same, only in this case I have 9 marbles sitting in here. And now by chance I actually picked the dark blue marble. Of course, at this point I actually win the game. So I place not 1 back, I actually place 3 back. And now you can see that the model actually starts to learn what is the right move here. Because the next time that I encounter this same state, I have a chance of 4 out of 13 to actually win this game. And the more I play this, the more this will skew towards only blue marbles. And of course, this is relatively simple because it's the end move. It's the last move of the game. But because we keep a state of every box that we've encountered, we can actually start creating patterns. And this computer doesn't even know anything about that. The end goal of the game is to get 3 in a row. But because we start reinforcing the machine towards winning moves, it will start optimizing to create multiple X's in a row. That's called a feature. So a feature of this model is that it wants to create things in a row, even though it doesn't even know what this is, or that 3 in a row is required to win this game. What you see here is that the training part here is relatively heavy, because I need to play hundreds of games and open boxes and put marbles in and out. It's very time-consuming. And you see that with a lot of machine learning models. The training is a really, really hard part. But after I've trained the complete model, if I have done all this work and I played 1,000 games and populated all the matchboxes, and then I tell to you, now please play a game against this machine, for you it's relatively easy. You just have to open the matchbox for every state, maximum 4, pick a random marble out, and put that move. And that's what we call classification. So using a completely trained model and not retraining it yourself can be done a lot cheaper than doing the complete training. I think that's something that we can actually leverage. So we started building a library called microtensor, which is a library specifically for machine learning on microcontrollers. So the first thing we decided is that we're not going to do training on this device, we're just going to do classification. So that is, you take a completely trained TensorFlow model, like all the Matchbox that we have, put that somewhere on a microcontroller, probably in external storage because this is a large model, and then we do that. So this is an open source library, Apache 2 licensed. And the fun part is, because we only do the training and we are highly optimized, we can run this in less than 256 kilobytes of RAM. You know, just now we were talking about AWS Lambda and how maybe 1.5 gigabytes of RAM is not enough. Scaling this down a little bit. Just to show you like what's the difference between training and classification, Google used 5,000 TPUs for training AlphaGo, but currently classification can be done on only 4. So that's a 1 in 1,000 split, just by not having to retrain. And this enables all kinds of really interesting use cases. For me, this is one of the coolest, sensor fusion. Because the whole IoT movement and the whole mobile phone movement, we've seen really cheap sensors coming into place. You know, I can get a light sensor for 20 cents. I can get sensors that measure like how much audio is being spread out for very cheap as well. But these are very limited sensors, very low quality. So as a company, they started building a super sensor by combining 10 sensors, training them all at the same time, and then combining the capabilities of all these sensors, creating a very cheap but highly accurate sensor for all kinds of stuff that you can do in the house. For example, you put the faucet on, or your washing machine is done. It's a really interesting video. One of the other things we can do with machine learning on the edge is federated learning. If I have, this is what Google uses for their keyboard in Android. Like you have a standard model of the world, keyboard prediction model, and Google just pushes that to all the phones. But I would like that a model like adapts a little bit to me, so it starts learning like the people that I text most. But I don't want to send all my raw data to Google, nor do I want to wait for the connection to come back to actually get my suggestions. So with federated learning is that you have the base model, you refine it locally. That costs very little processing power, because it's just refining a little bit, not completely training it. And then you send the diff of that model back to Google, and Google uses the diffs from all these people together to actually improve their models. I think it's cool. One of the other things we can do is autoencoding. So as said, our model with the matchboxes doesn't know anything that 3 in a row is a good thing. But it starts, because we're training it, it starts detecting features where putting multiple X's in a row is actually good. You can use that for a lot of other things. So if you want to do, you can use a machine learning model running on the edge to actually start detecting the features that you're interested in. So for data that's very hard to compress, for example, audio, you can look at the let's say you want to do voice recognition, like who is talking to this person, or who's talking to the computer, and identify the person like that. Writing a proper algorithm to do that is really hard, but by looking at like the specific features in someone's voice, that can actually be compressed down quite a lot by having a lot of training data, and that's something that an autoencoder can generate for you. And after that, if you want to like expand on the other end, that means that you can decompress that data and get something that loses some quality, in this case, loses some detail, but actually still has, the representation over and the features that you think are actually important. And then, of course, everything that's has to be offline and self-contained. Image recognition, sound detection, motion analysis, everything that I don't want to send over to the internet. In this case, this was the cow that we actually equipped with the sensor back in Africa. So this is how it looks right now. So this is running on a 200 megahertz processor, running in about 100 kilobytes of RAM. So we can write on the touchscreen. There's a banana for scale. So press the button. At that point, it runs a handwritten digit recognition algorithm, and then tells you what number to actually write down. So what do we see here? So this is kind of the hello world of machine learning. This is the MNIST dataset, which was compiled in 1998. That consists of 60,000 images of handwritten digits, all rotated in the right way, scaled down to 28 by 28 pixels, and all black and white. So we threw this through a training model somewhere on an actual physical machine, so on a big machine. So the training is still hard. Training still takes a lot of time. Through supervised learning. And then push the trained model actually to our microcontroller. Now, what happens when we actually want to see what the number is that we just outputted? So we throw this through a multi-layer perceptron. It's a type of a deep neural network, and the reason why it's deep is because it has 2 hidden layers. You don't go straight from the input layer to the output layer, there's hidden layers, so there's magic happening. And this magic, that is the feature detection. So in one of these hidden layers, it will probably learn at some point that, well, if I see a line going from left to right somewhere in the top of the screen, that might very well be part of a 5. So that's the feature detection that's doing. So we start with neurons. In this case, every pixel is a neuron, so 784 input neurons. We have 1 output, and there's actually 10 potential outputs. Now, when we're training this model, you adjust the weights between the input layer and the hidden layer. So it starts to learn that if a certain pixel is being turned on, that might be attached to a certain feature, and that feature is then attached to maybe the number 5. So the weights of this is like a big matrix multiplication table, a lookup table, if you want. We're just going to look, okay, well, this is a 1, this is attached to this other neuron with a certain weight, so I multiply it, I run an activation function, and this is how it goes through the network. And because it's backpropagation, we actually start with the outcome. We say, well, this example image is an 8, and you're going to adjust all the weights working backwards. Now, if we want to run this on a microcontroller, the hard part is, or what we actually need to load into memory, is this combination of the input elements in the first hidden layer. because all of these are connected. So we have 784 input neurons, 128 neurons in the first hidden layer, and these are interconnected. And that weight table, that's something that we need to keep in memory. Now we optimize the hell out of this, so we can actually have 1 byte per binding, but it's still almost 100K. But by doing that, we can actually see that we can fit the classification of this whole model in just 100K of RAM, which I think is tremendous. I think it's really cool. And that means that all of a sudden, running this model, even on your smallest devices in your household, starting to become possible. The speed is still not completely optimal, so that's what ARM is working on with CMSSNN. These are highly optimized code, specifically for calculations that you want to do for a machine learning model. So if you're doing image recognition, the idea of like using a single pixel as an input neuron doesn't really scale, because generally these are pretty big. So even when doing object recognition in images, we try to scale it down to 32 by 32 pixels. But these are all colored. So all of a sudden your whole model starts to blow up. So what you want to do is convolution and then pooling. So you kind of take the average of pixels that are going around. But these are relatively heavy calculations that you need to do. So we've written really optimized code, DSP and SIMD, if anyone has ever done assembly for Cortex-M devices. And then we see a nice speed up. And all of a sudden, stuff like image recognition becomes also feasible in these devices. So this is a demo running on a Cortex-M7, 200 megahertz, running in 150 kilobytes of memory. So we have an image of the webcam, we scale it down to 32 by 32 pixels, throw it through a model, and then here we have the classification. So most of the times it knows it's actually a frog, and at some point it's going to switch to kitten. Oh, cat there. This is brilliant. This is really running on a $2 microcontroller. Actual object recognition. It's like, how cool can this be? And actually, the speed is pretty great now as well. So we can actually run this in 100 milliseconds. This is tremendous. Like the time that it takes me to do classification on this really cheap, dirt cheap microcontroller is smaller than the time it takes me to upload this image to Google and have Google tell me what the actual conclusion of this is. And this enables so many incredible new use cases. That's why I'm really happy to be working in this field. So the team that I'm running also runs Embed Labs, and in Embed Labs, we kind of like, if we see an interesting project that we think that 2 years down the line is going to be important for our company, or is going to be important, like bigger in the whole Internet of Things world, we can incubate that. And this project came to me about 6 months ago by one of our Taiwanese engineers who just started hacking on this in their spare time, and I was like, yes, please come work for me directly. That's cool. I'm excited about this kind of things. It enables so many new use cases. So, last minute, let me recap. Machine learning in general is just incredibly cool. Even if it's done on really big data centers, on clusters, but almost every hour we use some machine learning already. Every time you use on your iPhone or Android phone, you use the prediction algorithm, that's machine learning. There's all kinds of stuff in your house is starting to learn, it's also machine learning. It's already everywhere, and even as like high-level developers, which I know that a lot of you are here, and I'm kind of that as well. We've not seen that whole revolution happen, but already, Google started hiring machine learning experts already 10, 12 years ago. But all of a sudden, because there's now tooling being developed, like a lot of the machine learning tooling is written in Python. All of a sudden, it becomes feasible for us to actually work on. And as long as we get enough data, we can actually run that. I think that's amazing. I think machine learning, this is the right moment to actually start hacking on that, even if you're a Python developer, even if you're a JavaScript developer. And the ability to actually push that down to microcontrollers and actually have your model that you just trained in TensorFlow in Python, but now be able to run it on even the smallest of your devices in your house, that is even cooler. So if you want to get started, we have a bunch of dev boards. They start at like $12 or something. The actual chips on them are $1.50, $2. So build a dev board, buy a dev board, clone microtensor. I don't know what's going to happen after that, but profit. Right, so with that, thanks a lot. And more information on labs@embed.com.
Thank you, Jan. And I think with the time we have left, we could fit one question, maybe two. There's somebody in the back. Could they get a microphone?
It's good for the video as well if there's on the mic.
Yeah, like your presentation was mainly focused on the coolness of machine learning and positive sides. So I would like to ask, for maybe for everyone, what is the main challenges and for machine learning on edge and for IoT in particular right now?
I think that the main challenge with every machine learning model at the moment is that it's very hard to know if you trained the model right. So do I get the right question? Do I get the right answers from my model because I modeled my my neural network in the right way, or was this just chance? Am I overfitting or am I underfitting? And even if I know that that is all correct, it's a lot of like trial and error in this case. What is the shape of my network? What does it have to be? Is my data set not inherently biased? One of my acquaintances, he's working on bias detection in neural networks. So they got at some point a set of data from the police in the US, and they started using that to actually start profiling people. But they realized quickly that the data set they got, based on like historical data, was racist. And all of a sudden they built a racist neural network where they try to remove the bias. And how can you detect something like that if your base data is inherently flawed? And I think there's going to be a lot of really interesting development in there. But that's something we're going to see in the next couple of years. It's
what you said right now is really general in terms that it applies to the entire field of machine learning and like explains the results and detecting bias. But what is specific to edge computing, to the devices and IoT?
Specific is what we need to do is make sure that this all, 3 minutes. Like fitting all of this on a device is kind of hard because your trained model is large. So we're looking at like ways of like splitting that up. Right now we just dump everything in Flash, but that's relatively slow. After that, like a lot of the sensors that are on these IoT devices are very jittery. So getting proper data out of that is already hard. So it's very much in the first phases of development. So we're going to figure that out. I'm happy to talk with you later about this.